and please get started.
Thank you, Sam. So today I wanted to present two projects that I've done in my second half of my PhD, which are about applications of piecewise deterministic Markov processes with boundary conditions. And this is a joint work with my former supervisors for my PhD and also my current supervisor of my postdoc. Okay. So let's see, yeah. This presentation is structured as follows. So I will start with introducing PDMPs. Then I will talk about PDMPs with boundaries. And I will talk in particular about three different types of boundaries. The first one I informally called sticky floors. Essentially, a sticky floor is a boundary for which the process, when it hits the boundary, it will stick on it for a random time. And these turn out to be very useful for Bayesian variable selection. And I will show also a nice illustration of this. The second boundary is there are soft or hard walls. I think these are self-explanatory, meaning that when the process hits those boundaries, it will either cross the boundary or reflect. If it's a soft wall, it will cross it with positive probability. If it's a hard wall, it will just reflect on the boundary. And here I have a non-trivial application, which is sampling the latent space of infection times in the SIR model with notifications. So this is a interesting problem in epidemics, which it's my understanding that usually MCMC algorithms, they really struggle on this application because they have poor mixing, and also they scale badly with the population size. So by using PDMPs, we try to solve these two problems. And finally, there is a last kind of boundary, which I call the teleportation portals. Essentially, when the process hits the boundary, it will teleport somewhere else in space. So in some way, PDMPs are continuous in space processes. And by introducing these teleportations, then we can let the process jump in space. And here, as an illustration, I have I sample from the invariant measure of hard sphere models, which are sort of problems which are interesting in statistical mechanics. All right. So the preliminary is the usual. I have a parameter x in RD. We have a prior measure mu0 and the log likelihood L. And then by applying the Bayesian rule, we get a posterior. And we run a Markov chain for approximating this posterior. So our Markov chain XS will converge in distribution on to mu. And we can approximate the integrals relative to the posterior mu with just time averages of our Markov chain. So we can use a sort of law of large numbers. And in this framework, let's say the constant of proportionality C is assumed to be unknown. Now, our Markov chain is a continuous time Markov process, which is a piecewise deterministic Markov process. So in this animation, you can see three different PDMPs. They all have deterministic trajectories, piecewise deterministic, and they have random events, which are the blue and the pink dots. At these events, the process just change direction. And the nice feature of these processes is that they are conceived and also simulated in continuous time. And these turn out to be extremely useful when we have boundaries. These are just the standard PDMPs, so there are no boundaries here. And they are used to sample distribution which have a density relative to the Lebesgue measure. They also have very nice theoretical features, properties, because so they have a momentum variable and they are non-reversible. And this is shown that in some cases it implies fast convergence to equilibrium, and also lower asymptotic variance in the central limit theorem. Now, so here I distinguish two kind of event times. One are reflection, and the other one are refreshments. The reflections are used to target the right distribution, and the refreshments are sometimes they are there, sometimes they are not. For example, in the zigzag, we don't have refreshments, and they're used to, they're sometimes necessary for having ergodicity, for exploring the whole state space, right? So now, more mathematically, we have the process is as a state space RD for the position and a velocity space. So it's the product of these two. We have to define deterministic dynamics, which are given by a ODE. And in this talk, I also wanted to introduce this little function S, which is referred as speed up function, which essentially doesn't change the direction of the ODE, but only the intensity. So essentially the magnitude or the speed of the process changes with this function S. And then we have also, of course, associated solution of this ODE, which is phi, and this operator, which will be used afterward, which is just, uniquely is defined by the ODE. Then we have we have to define the frequency of our random events, which are given by a Poisson rate. Essentially, the first event time is distributed as a inhomogeneous Poisson process. So it's the first event time is given by this probability, where the lambda rate is evaluated along the deterministic trajectory. And finally, when there is an event, we need to tell the process what to do. So we have a Markov kernel, which for PDMPs acts only on the velocity components, because if you remember the animation, the process doesn't jump in space, but just changes velocity. All right, and we can combine different events. For example, before I told you there are refreshments and reflections, and these are nicely combined by summing up the event rate, the lambdas. And then also, if we have, for each event, we have a transition kernel, then we can just define the overall transition kernel as a weighted sum of the transition kernels. Now we have all the ingredients, and we can write down an operator, which is the extended generator of the process, which is, as you see, there is the green part, deterministic dynamics, the frequency of the event times, and what happened at event time. It's just an operator which acts on function on a suitable class of functions. And then for proving a necessary condition for the process to have a given invariant measure mu is that the integral of this operator a on all the function in this class relative to the measure mu has to be equal to 0. So this needs to be verified. Right, now let's move to PDMPs with boundaries. So the formal setting, there are two papers which discuss rigorously about PDMPs samples with boundaries. One is the original book of Davis, and the other one is a recent work where, Sam, Paul, and other people in the audience are co-authors of this paper. So they treat in a rigorous way this setting of PDMP with boundary conditions. For now, in this talk, I'm assuming that there is a target mu on RD, and we have some boundaries, like I drew here, which are piecewise smooth manifold in dimension d-1. So you can, in R2, they are just lines. Now we have to differentiate between entrance boundaries, which are points at the boundary where the process hits the boundary, and the exit boundaries, which are points on the boundaries where the process leaves the boundary. Okay, this is just defined by this inner product with the normal vector at the boundary. And notice that there are two copies of the boundary in this setting. All right, what we need to do is essentially to define a kernel at the boundary. So we need to tell the process to map every point on the boundary, on the entrance boundary, to points on the exit boundary. So the process stays in let's say in the space. Now I will talk about the sticky floors. So the first kind of boundary. So the sticky floors, as I said, are used for targeting measures that arise in Bayesian variable selection, and especially for sparse problems. So sparsity in the Bayesian framework means that there is prior information that some parameters are exactly 0. And this can happen in several situations, for example, for variable selection, or when we have an overspecified problem. In all these settings, so we must have a prior which is supported in any lower dimensional subspaces of RD of this form, where some parameters are exactly 0. For this alpha is a subset of the indices. Now, if you think of the standard prior measures that we use, for example, Gaussian, which has a density relative to the Lebesgue measure, this is not a good candidate because that's zero mass on these lower dimensional subspaces. And maybe one of the most famous prior measures used for Bayesian variable selection is the spike and slap prior. So this is a product measure. And with probability under this prior, with probability Wi, the height component is exactly 0. So this is a Dirac measure at 0. And with the remaining probability, it's as a density relative to the Lebesgue measure. It's very simple and easy with a nice intuition. Now remember that we want to estimate this integral of the posterior of the measure mu. With this time integral of the Markov chain. And if we have this sort of priors, also the posterior will be supported in these lower dimensional subspaces. And yeah, so if we want to estimate the posterior in this way, then the process needs to explore these subspaces. Otherwise, we are in troubles. So the standard PDMPs are not good for this purpose. We need to do something, and what we did is something extremely simple, which is to introduce sticky events. So essentially, the process is the same. This is just an illustration of one coordinate. This is the standard PDMP, and this is what we do with introducing sticky events. So essentially, every time the process passes through the point 0, it will stick at 0 for a random time. That's it. And then after this random time, it will leave 0 on the other side of the interval. So this is a very natural idea, and it allows the process to explore these subspaces, M alpha. And there is still one question, which is I didn't answer, which is how much time should the process, should every coordinate stick at 0? All right. Now, again, let's talk a little bit more mathematically. So as I said before, we need to have two copies of the boundary. So we have here 0 minus and 0 plus. And we define this boundary for the coordinate, which is either 0 minus with positive velocity. So these are the entrance boundary. So the boundary for which the process hits the boundary. So either with negative, on 0 minus with positive velocity, or on 0 plus with negative velocity. And then we just need to define a transfer mapping, which maps every point from one side of 0 to the other side of 0. And finally, the generator in the domain is straightforward, because we have the same generator as the standard PDMP, but then we need to add some additional condition on the class of functions. where the generator acts. Most importantly, we need this boundary condition. So if you are not really used to look at the generators, this is just saying that at the boundary, the process jumps from the boundary to the other side because we apply the transfer mapping. After holding time, which is kappa I times the modulus of the velocity. That's it. Now, a rigorous proof for the invariant measure of this process is quite technical, but what I can tell you here is that if we compute this integral with the generator applied to this class of functions relative to a measure mu times, this is the measure of the velocity component, the invariant measure of the velocity component, then we see that this is equal to 0 when mu has this form. So essentially, if we just forget about C, the constant of proportionality, we have the same measure as before, but we have an extra bit here, which is a Dirac measure at 0, with, which multiplies a term 1 over Ki. And it turns out that this is so this is a large class of measures, and for example, posteriors with spike and slap priors and smooth likelihood they have this form. So you can use the sticky PDMPs for sampling posteriors with spike and slap priors. Now, as an illustration, I have this spatially structured sparsity, so an image which is observed with white noise. This is a very huge dimensional space because the picture is 1000 by 1000. I think there is a 0 missing here. But so the dimensionality of the process is 1 million, okay? This is what the ground truth. So the picture is black almost everywhere, and there is a little heart in the middle. And this is what we observe, okay? Now, for this problem, we don't want a spike and slap, because we also want to assume that pixels, neighboring pixels are correlated, right? So what we have a Gaussian density, where gamma is the Laplacian operator. So essentially is the precision matrix which correlates all the neighboring pixels. And then we have this blue part, which essentially enforces a sparse solution because there is a Dirac measure at 0. Okay, so this is I think the posterior mean, and on the right half there is the error between the posterior mean and the ground truth. So essentially we make no error when there is a black background, and we make some error in the boundary. This is I think a problem not of the sampler but of the Bayesian procedure. And then we make a little error in the image. And here is just a segment of the PDMP. In this case, I use a zigzag. So these are two correlated coordinates, and this is one coordinate which was black. So it stays almost all of his time at 0. Right. So now just a few remarks. The first one is that this problem is not easy because we had to implement something which like a 1 million dimensional process, which is not easy to run in a laptop. Think of that the precision matrix gamma is as a trillion of elements, and also this model selection. So we have to select a model, and here there is a extremely huge number of models. Things that, for a reference, these are the numbers of atoms in the world. So it's much bigger number. The trick is essentially that the sticky zigzag behaves locally as a lower dimensional zigzag sampler. So we never run a 1 million dimensional process, but we always run a lower dimensional process, which is cheaper, computationally speaking. And just to mention that we really exploit the continuous dynamics of PDMPs, because many the standard MCMC, which are discrete time process, they jump, and that makes I think that makes more difficult to formalize this a setting similar to this. And indeed, for discrete Markov chain Monte Carlo, they requires proposals to jump between these models. But if there are many, many models, then it's difficult to come up with a good proposals, which works in general.
5 minutes.
Yeah. Oh, yeah. Okay. Then I should hurry up. So yeah, this is just to say that since it's difficult to run MCMC for variable selection, what people do is to approximate the spike, the Dirac measures, and with a continuous component, and then just run your favorite MCMC. In this case, it wouldn't work because a 1 million dimensional process just doesn't run. Yeah, so one limitation of this approach is that the posterior has to be supported on all the neighboring models, because the process cannot jump between two models which are not close to each other. Okay, now I'm going faster. So I think I will skip teleportation, the illustration with the teleportation, but I will just talk about hard and soft walls. As I said, soft walls are boundaries where the process can just cross them. Sometimes it doesn't cross them other times. And we have a very clean theory with these things, which is based on a skew detailed balance condition. Maybe there are a few people that are interested on this. Maybe I can talk with them afterwards. So essentially, the process, if the kernel at the boundary satisfies the skew detailed balance condition relative to a sign measure, then the PDMP has the right invariant measure. And we can set up a metropolis hasting where we just need to define a kernel on the boundaries. And then we can, this also includes teleportations. So this kernel can let the process jump from one place to the other of the boundary. And the speed up velocity, piecewise constant, can somehow make sure that sometimes, not always, that the probability to accept a new point on the boundary is equal to 1. So you can offset this probability by using the speed up function. Now, it is the only illustration, only application I will talk for today because I don't have time. So it's the SINR model. So it's used for emerging infectious diseases. So the process is a process on this label. Every individual can be either susceptible or infected or notified or removed. And the people get infected according to a Poisson, inhomogeneous Poisson process, essentially. Okay, and then we also assume that the delay between infection and notification follow a distribution F, capital F. Right, so what we observe is just the notification time. So here I just simulate the model forward. The dashed line is the infection times, which we do not observe. We only observe the solid lines. So here on the x-axis is the time, and on the y-axis, all the individuals. So this is the simulation of all the individuals. And we use the PDMP to sample from the infection times minimum with the capital time T. So in essentially, by doing that, if the infection time is at T, then it means that the individual is not infected, is at the observation time capital T is susceptible. So T is as an atomic component, so is a sticky floor, where if the trajectory is there, that means that the individual is not infected at that moment. All right, and here there are a lot of discontinuities, so a lot of hard and soft walls, if you want. And then we can also just take compute the empirical marginal densities of the infection times. And you see here, I took 4 different people that are at time capital T were either susceptible or infected or notified or removed. And you see that like one was, for example, the last 2, we have the same observation, namely nothing. But we can somehow say with some confidence that one was susceptible at observation time and one was infected. Yes, so these are just remarks, which concludes my presentation. Most importantly is that I think both the heating times and the reflection times are somehow local. So they scale linearly with the complexity of the algorithm. So I'm wondering, and I'm very curious to understand if the algorithm scales linearly with the population size n. Then, of course, this is a part of the problem. The other problem is to do parameter estimation of this model. And yeah, I just leave it here with with this animation. So essentially, with the teleportation for this kind of model, hard sphere models, we just swap the balls where they hit each other. And in this way, we can enhance mixing of the process, essentially. Yeah, so here is just a trace plot which shows that the mixing is better when we do teleportation. Yeah, thank you very much.